Enzymes, the biological catalysts that facilitate countless biochemical reactions, are highly sensitive to their environment. One crucial factor influencing their activity is pH. Investigating how pH affects enzyme activity helps us understand enzyme functionality and optimize conditions for various applications. Formulate a hypothesis. Start with a clear hypothesis, such as the activity of enzyme X will peak at its optimal pH and decrease at pH levels above and below this optimum. Select the enzyme and substrate. Choose an enzyme and its corresponding substrate. For instance, if investigating amylase, an enzyme that breaks down starch, the substrate would be starch. Prepare buffer solutions. Create a series of buffer solutions with different pH levels, e.g., pH 3, 5, 7, 9, and 11. Buffers maintain a constant pH, ensuring the enzyme is exposed to the desired pH throughout the experiment. Experimental setup. In each reaction tube, mix a fixed amount of enzyme solution, substrate solution, and buffer solution of a specific pH. Ensure all tubes have equal volumes to keep the experiment consistent. Control conditions. Maintain other conditions like temperature and enzyme concentration constant to isolate the effect of pH on enzyme activity. To measure the enzyme activity at different pH levels, use a suitable method to track the reaction progress. One common approach is the spectrophotometric assay, which measures changes in absorbance related to substrate conversion or product formation. Initiate the reaction. Add the enzyme to the substrate buffer mixture to start the reaction. Monitor the reaction. At regular intervals, measure the absorbance using a spectrophotometer. For example, if the reaction produces a colored product, the absorbance at a specific wavelength will increase as the product forms. Record data. Collect data on absorbance changes over time for each pH condition. Calculating the rate of reaction. The rate of an enzymatic reaction can be calculated by determining the change in concentration of substrate or product over time. Plot absorbance versus time. For each pH condition, plot the absorbance values against time to create a reaction curve. Determine initial rate. The initial rate of reaction is the slope of the reaction curve during the early linear phase, where the reaction progresses at a constant rate. Convert absorbance to concentration. If needed, convert absorbance changes to concentration changes using the Beer-Lambert law, which relates absorbance, A, to concentration, C, through the molar extinction coefficient, A, and path length, L. Compare rates across pH levels. Compare the initial reaction rates at different pH levels to determine the enzyme's activity profile. The pH with the highest reaction rate indicates the enzyme's optimal pH. Graphing activity versus pH. Plot a graph of enzyme activity. Initial rate against pH to visualize how activity changes with pH. This graph typically shows a bell-shaped curve with peak activity at the optimal pH and decreased activity at more acidic or basic pH levels. Enzymes have an optimal pH at which their structure and function are most stable and efficient. Deviations from this optimal pH can lead to changes in the enzyme's structure, denaturation, or alter the charge of amino acids at the active site, reducing the enzyme's ability to bind substrates. For example, at low pH, acidic conditions, excessive hydrogen ions, H+, can disrupt hydrogen bonds and ionic interactions, denaturing the enzyme. At high pH, basic conditions, hydroxide ions, OH, can similarly disrupt enzyme structure and function. Understanding the effect of pH on enzyme activity has several practical implications. Industrial processes optimizes conditions for enzyme-based reactions in industries like brewing, food processing, and pharmaceuticals. Medical diagnostics design enzyme assays for clinical tests, ensuring they operate at optimal pH for accurate results. Environmental studies study how environmental pH changes affect enzymatic activities in ecosystems. By carefully investigating how pH influences enzyme activity and calculating reaction rates, scientists can unlock valuable insights into enzyme functionality. This knowledge not only enhances our understanding of fundamental biochemical processes, but also drives innovations in various scientific and industrial fields.